Okay, so I don't see the starting. Okay, anyway. So again, good afternoon to everybody. Today I will try to discuss some important epistemological and historical problems and questions which are necessary if you want really to understand how mathematics works in modeling physical phenomena. Of course, I must specify my general talk using some specific examples of phenomenology, so phenomena, and mathematical models for describing these phenomena. So what I decided to consider, I decided to consider standard ideas in continuum mechanics. Continuum mechanics is the theory of deformable bodies. And this theory will be the subject of many of our lectures. Some interesting phenomenology in continuum mechanics is given by this nice picture. So I want to show you how beautiful is the field showing you this picture. You know, this is a picture of a transparent body whose refraction index depends on the deformation state of the body. So if you have a light behind it, you see different colors in different positions where you have a state of deformation. So this picture, I mean, this is a specific material. It is called photoelastic material. There are some few materials that have this nice behavior. So their optical properties depend on the state of deformation. And these pictures were used before the invention of digital computers for a kind of analog computing. So for instance, if you want to know how a sheet of metal behaves when you pierce 10 small holes and a big hole in the center, you can try to get an idea of this deformation phenomenon deforming a sheet of photoelastic material, and you can shoot a picture. Okay, so these are one class of phenomena and mathematical problems related to these phenomena we want to discuss. Another one is the apparent motion of planets, stars, moon, sun with respect to the Earth. Okay, this is an ancient phenomenology. You will discover that it is very old. And I think that you can get an interesting series of informations and observations while discussing the development of this mathematical model in the centuries. Okay, and I will establish a parallel between the social phenomena occurring to the mathematical model used for describing the motion of planets and the mathematical model used for describing deformable bodies. So this will be another interesting subject which I will touch during these lectures, the whole course. Okay, the title of this presentation now is From the World Reality to the Model, which is the healthy process. One observes reality and then he tries to invent a mathematical model for describing the reality. But we have also a very interesting phenomenon we should discuss, which is the other step, from the model to the replacement of the world reality. What sometimes happens in applied mathematics and in engineering is that very often engineers and applied mathematicians are confusing the mathematical model with the reality itself. And I will try to describe you in a better way what I mean in this lecture today and tomorrow, maybe also next Monday. Another subtitle is the materialization of the Eudoxus model for the motion of planets and of the abstract concept of force and internal tension. So what I want to underline is that a materialization phenomenon occurred before Middle Age, which made the model for planetary motion to become these kind of structures and then reality in the mind of people. This materialization phenomenon is also occurring now in modern physics, and some theoretical engineering scientists are inventing or conceiving or are confused by this materialization process, the materialization of the concept of force. Okay, so you understand that I will soon, no, maybe at the end of this lecture or at the end of this series of lectures, will criticize the way in which the word force is used. Okay, and this, I think it is better that we do this at the beginning of our classes, of our course, because in this way our process will, our lectures will flow more smoothly. Okay, what I will present in this first part of this lecture is the reconstruction, which is partly conjectural, of the birth and decline of the Greek mathematical models for planetary motion. Okay, and the scheme which I'm showing you here, talking about the solar system, is a schematic way for describing the motion of planets as conceived by, I would say, Copernicus. Actually, we should say Aristarchus of Samos. Okay, we will discuss later this. But are we in Greek epoch? Were we the first? We, I mean, Western scholars. By the way, I'm not talking about Western scholars as some genetic characteristic. Okay, I just start telling you that we had Roman emperors which had black skin. Okay, in the classical Hellenistic Greek and Roman epoch, there was nothing like any racial distinction between people living in the empire. At the end, everybody was citizen of the empire. And don't forget that more than 1/2 of the Roman Empire was in Africa or Asia, while a big part of Germany was outside the Roman Empire. So when we talk about Greek and Latin science and civilization, we mean something in which you have already an important melting pot. By the way, in Nebra is a place in Germany outside the Roman Empire, by the way, 2000 years before Christ, they produced this disk. And on this disk, you can recognize half a moon, a full moon, then you can recognize the Pleiades constellation, so the stars, and many stars placed in this scheme. So in a sense, this is a kind of chart of the sky, okay, a map of the sky, okay? So what they were doing they were describing the position of the stars in the sky, and they were describing somehow where the moon was growing and where the moon was full, in a sense, or declining and full. Okay, so in this first stage, the scientists of this Bronze Age civilization started describing the position of stars in the sky. Okay, now you have a second stage. The second stage is to use this map of the sky in order to have a forecasting use. Okay, they were using this disk in order to get predictions. Okay, what they were doing most likely? The set of the stars at west before the sunset, okay, constituted in alternated periods by Pleiades in the Bronze Age, was coincident with the crescent moon, which means March the 10th, or with the full moon, October 17th. So this tool was telling you something like that. When you see at sunset Pleiades, okay, and you see crescent moon, you are in March. If you see at sunset Pleiades at west and you have a full moon, then you are in October. So even if we don't have anything written, we could deduce that this disk was used for determining the calendar of some agricultural activities. What I want to tell you with this, that observation of periodic repetitive phenomena has been elaborated since 2000 years before Christ in order to predict future phenomena. So do you want to know if it is the moment to start agricultural works like seeding or anything which should start in spring? Okay, you use this disk, you check if Pleiades are at west and if you have the half moon, and then you can deduce that you are in spring. So this was a tool for predicting. Please consider that this very elementary process is being repeated in every scientific process model formulation, including the most complicated one like general relativity. Then you have an increase of the sophistication of your disk. Why? Because they glued two angles, 82 degrees, always made of gold, okay? And they most likely used these golden angles for doing this nice work. Look at this small picture here. Okay, if you place your disk with the orange line from the Mittelberg Hill and the Mount Brocken, like this, okay, you can see the solstice indication, which is here, okay, one solstice. And then you see the equinoxes when the sun is rising here and the sunset is there, okay? And when you are here, so when the sun is rising there and the sunset is there, you have the other solstice. By the way, solstice is the day when the day is lasting the longest period of the year, or the lowest period, because you observe that the length of the day is a periodic function. There is one day in which the light is lasting the maximum, another day when it is lasting the minimum, and you call it solstice, while equinoxes are when the day is exactly equal to the night. Okay, so the orientation of this disk was allowing this civilization to forecast in which period of the year you are, because you check where in this angle the sun is rising. Once you have oriented this orange line from one mountain to the other one, then you can predict in which day of the year you are. So in a sense, you get a computer calculating the day of the year, just checking where the sun is rising. Okay. Then you have the religious degeneration. You have the decline of the society and the transformation of the scientific instrument into a religious object. Probably after a while, the teachers did not manage to be followed by willing students. So soon the use of this object became impossible because they did not know which was the meaning of this disk, so that, as the tradition was telling that this disk was very important, they transformed it into a magic tool. They glued another golden small sheet there, which is the solar ship, and they buried this object in a tomb. Now, you should remark that the gold constituting the stars and the moons has a purity greater than the one used for the horizon arcs, which have a later and different origin, and they are also greater than the one used for the solar ship. You keep having a later and different origin in this gold. Okay, so we can know for sure that the solar ship and the arcs are more recent. So what I want to tell you is that the story of the disk of Nebra shows that it is not true that science is always increasing in power capacity, that knowledge is not only a bare addition of information one year after the other, but that at the end of the story, you have growth and decline of societies, of scientific societies. Okay, so let us talk about another powerful scientific society and a very important person in this scientific society. So starting from 428 before Christ, so millennia after Nebra disk, we meet Archytas of Tarentum. Archytas of Tarentum is probably the inventor of modern mechanics. At least Archimedes claims that Archytas of Tarentum was the first mechanician using mathematics for describing physical phenomena. Okay? We know that Archytas of Tarentum wrote a book Now, I want to tell you how this book is arriving to us because it is an interesting story. This is the first page of a book written by Bernardinus Baldi, where he claims that he's translating into Latin Mechanica Aristotelis Problemata, which means mechanical problems by Aristotle. Okay, so now you could ask me why you are telling that Archidas of Tarentum was the author of Mechanica Problemata, while in every copy we have of this book, it is written that this book is due to Archimedes. Okay, sorry, to Aristotle. Okay, this is a complicated story. I will make it short. Maybe I will give you more details later. But my interpretation, together with the interpretation of several famous historians of science, is that this book was considered too complicated mathematically in a given moment of history. Okay, so as is done nowadays very often, you know, when I'm teaching to engineers, but also to mathematicians, I'm very often told that I should be slow, I should explain slowly, don't do too much complicated mathematics, otherwise your students will be upset and they will abandon the course. Okay, so what happened is that Aristotle was considered the best scientist of the past. Okay, so a copyist decided to say that Mechanica Problemata was written by Aristotle in order to save it. You know, the idea was, I say that this book is written by Aristotle so that people will keep copying it even if it is difficult mathematics. Aristotle, in many other books, wrote that he doesn't understand at all mathematics. Okay, so it is really ridiculous to think that this mathematical object could have been introduced by, written by Aristotle. Okay. On the other way, we know via some Latin encyclopedias that Archidas had written a problem about a book about mechanical problems. And using some stylistic properties of the Greek text, which arrived up to us, many scholars managed to understand that it is due to Archidas the invention of the principle of virtual work and its application to the study of the equilibrium of levers. So why I want to underline for you now that in the 4th century before Christ, using the principle of virtual work, the first ideas of mechanics, mathematical mechanics, were developed using the principle of virtual work, and in Greece and by Archidas of Tarentum, because in this book you don't find any single concept like force. So I am strongly interested in proving you that you can develop statics without introducing the concept of force. So this is the first important thing. The second important thing is another one. I want to invent new models. I want to teach you to be original in inventing new models. I would like to have among you many PhD students. Okay, And I want to, before I retire, I want to invent some other nice model, hoping that I will have next time a better idea than I had up to now. I want to see how mechanics has been formulated at first in order to learn how to invent in the appropriate way a mathematical model. Because unfortunately, as we will discuss later, up to now, there is no such a recipe ready for inventing mathematical models. We still need to teach mathematical modeling as happened for the painters or sculptors during Renaissance. In order to learn how to become a painter, Michelangelo had to go to learn in the workshop of another painter. Okay, so the way in which we are inventing models is not following a recipe. Actually, we must see how mathematical models were invented in order to understand which is the true good idea, the good process, the procedure which developed the most efficient mathematical models. Archytas of Tarentum is considered a mathematician, first of all, and you know it is attributed to him the invention of a trick track. A trick track is a device where a flange is oscillating, producing a sound. So probably Archytas was inventing this toy for proving a physical phenomenon, that sound is produced by a vibration of a chord. You know, in this epoch, Greeks were inventing the modern theory of instruments. Okay, so probably some acoustic was being understood by Archytas. By the way, Archytas became an administrator of the state. This is also a phenomenological aspect which merits to be remarked. This phenomenon that a mathematician becomes an administrator of the state happens sometimes in history when a society really needs somebody who has some competences. By the way, Mario Draghi is not a mathematician, but he was professor of economy, and his research was deeply founded on mathematical roots. So after French Revolution, this started to happen also in Europe another time. A pupil of Archytas is Eudoxus of Knidos. He was a mathematician and an astronomer, and he is considered the father, one of the fathers of mathematics. He studied, now you must be very careful in understanding this. He studied the problem of finding the algorithm using ruler and compasses for the duplication of the cube. All his works are lost, and we have only secondary sources. According to Archimedes, he is the inventor of the concept of real number in its geometric definition. Many among you, I hope, heard about Dedekind sections of rational numbers needed for defining a real number. Okay, I will give a quick lecture about this in the future, in one of the future lectures when we talk about approximation. I want to make you understand why the problem of the duplication of the cube is so important, was so important. So the problem is the following. You have a cube having side 1, and the volume is 1. Then you have a cube whose volume is 2. And you want to calculate the side of a cube having volume 2. Okay, so you need to, starting from this segment, you need to build a segment which is cubic root of 2. Okay? Now, if you already have real numbers, you may believe that Eudoxus was a naive, stupid person who did not manage to understand that you need to calculate the square root of the cubic root of 2 in order to get the solution of his problem. Actually, he wanted to find an algorithm, so a sequence of steps for constructing the cubic square of 2 using ruler and compass. Why? Because the computing tool used by Greek scholars were rulers and compasses. Okay. Now, you should know that cubic root of 2 is not rational. It is not a rational number. Okay. So you should know that there is no possibility to subdivide 1 in a finite number of parts, then multiply this part times another natural number for getting exactly this side. So you are not surprised that Eudoxus of Cnidus was the inventor of the concept of real number, because he was the first probably to understand the incommensurability of some segments, and in particular the incommensurability of the cube having volume 1, the side of the cube of having volume 1, and the side of a cube having volume 2. So, by the way, there is only secondary sources. There are only secondary sources talking about Eudoxus. I forgot, I think it is worth I go back, that I repeat that here we are doing only a conjectural, partly conjectural reconstruction of the birth and decline of the Greek mathematical models of planetary motion, because we don't have all the sources. In particular, we have lost Eudoxus of Cnidus books. By the way, in an encyclopedia written during Hellenistic epoch, which is called Sudas, there is an entry in which the name Eudoxus of Cnidus is cited. You know, encyclopedias were available already the 3rd century before Christ. And in this encyclopedia arrived to us. And in this encyclopedia, there is the list of the books written by Eudoxus of Cnidus. These titles are Eclipses of the Sun, Octaterides, which is a cycle, lunar solar cycle lasting 8 years, Phenomena and Entropon, which is spherical astronomy based on observations made in Egypt and at Cnidus. This suggests us that Eudoxus moved to Alexandria to work in the famous library. Okay? And very important, in motion, or motion of planets. And I would be ready to pay even 1 million euros to have in my hands this last book, because probably this is the beginning of modern mechanics. Okay. By the way, Theodosius of Bithynia, which is a later writer, probably wrote Spherice, a book about spherical motions, okay? which is a kind of plagiarism of the work of Eudoxus of Cnidos. Okay, and Eudoxus wrote also, it is written in Suda, an astronomical observatory. But the fame of Eudoxus is related to the homocentric spheres model. This is a model of a universe divided into spheres with a single center of rotation. This is a schematic drawing of the Eudoxus model. At the center, Eudoxus placed the Earth, surrounded by spheres in uniform circular motion. The outer sphere contained so-called fixed stars. You know, there are some stars whose relative motion is always, relative distance is always the same as observed from the Earth. And when you move 1 year around the sun, but you know, the definition of year has been already given. Look, it is given here. 1 year is when the sunrise starts here, arrives there, and then comes back. Okay, this is what we could call solar year. Okay, so what is interesting is that the fixed stars are observed every day of the year, always in the same position, at least in the human lifespan. We will see that this is not exactly true. So Eudoxus was considering the outer sphere. You can see here the symbols of constellations. Okay, and then all the other planets or stars in motion were considered, their motion was considered as a composition of uniform circular motions. Now, let us try to guess why Eudoxus had this idea. Look at this picture. You know, unfortunately, this is not mine. I would have liked to have had the technical capacity. You know, I like in this period of my life, as I had a period when I was young, now I have another period when I am crazy about pictures, but it will last not so much. If you go in a desert in Australia and you place your camera in a certain position and you wait for a long period, then you can shoot this picture. Look, this is not a painting. This is not a painting. This is a picture. And these circles are the tracks of the stars as observed from the Earth. Okay? So, how did Eudoxus get the ideas of homocentric spheres? The answer is obvious. Look at the sky and you have this idea. Inspired by observation, he formulated a conjecture. So, in every source referring to Eudoxus, you never read that Eudoxus proved that the motion of planets is a composition of spherical motions. You always find words like postulated, hypothesized, conjectured. Okay. Now, what I want to underline for you, we will go back to this point later. He did not induce a theory. I want to tell you since now that mathematical theories are not induced by observation. A theory is conjectured. And after you conjecture it, then starting from your conjecture, you try to predict what you have observed, and then you try to predict what you have not yet observed. But we'll come back to this point soon. Okay. So what is doing Eudoxus? He can see complexity of motions in the sky. So in order to account for the complexity of the motion, for instance, of the sun and the moon, he invented 3 spheres. So you have one sphere, a second sphere, a third sphere, okay, a fourth sphere, because this is a planet like Venus, Mercury, Mars, Jupiter, and Saturn. So in this picture you have 3 or 4 spheres. You have a pivot connecting one sphere to the other, okay? Then you glue here the planet, and you have the motion of your planet, which is described as the composition of these 3 spherical motions, or 4 spherical motions, okay? So in the model of Eudoxus, you had 27 planetary spheres, 4 for each of the 5 planets, Venus, Mercury, Mars, Jupiter, and Saturn, and 3 each for the sun and the moon. Remark that the model does not manage to reproduce the retrograde motion of all the planets, and in particular that of Mars. So this is a first mathematical model which accounts for some phenomena and is not capable to predict any new phenomenon. However, it accounts for reasonably careful, it manages to account for reasonably for periodic motions of planets and in the sky, okay? Being a great mathematician, if we must trust Archimedes, Eudoxus was probably aware that his model was not coinciding with reality. Then we have another scientist, later scientist. Remark that these scientists are living, there is an overlapping or a nearly overlapping. So this man died 355 before Christ. This one was born 45 years later. So you need 2 generations of scholars for connecting one to the other, okay? So it is not a long gap. This is another important feature we must understand. And this is the reason for which, even if I was obliged to pass every student in my classes without examining them very, very carefully, I strongly want to work a lot of time with my PhD students, because I think that the only true way for transmitting knowledge in this moment, maybe humankind will invent better moments, better methods. This is one of the reasons for which I try to keep video recorded my lectures. The hope is that somebody who will not meet me alive may have some ideas hearing my lectures. But what I want to say is that science is growing only when you have a narrow connection between maestro and pupil, okay? In our generation, old people are considered, you know, I was a very strange generation. I had to be always very reverent towards my maestri, but my students are claiming that they can get better knowledge without interacting not only with me, because this is not serious, not important, but without anybody else. Okay, they claim that they can rediscover everything alone, and this is very dangerous. Okay, so let's go back to Aristarchus. He is called the ancient Copernicus. This makes me very upset, extremely upset. Okay, because why should not we call Copernicus the modern Aristarchus? Aristarchus was formulating heliocentric theory. Of course, the work illustrating heliocentric theory has been lost. We know only few fragments in secondary sources. Okay, so we know in many sources some fragments telling that Aristarchus had invented the model of heliocentric planetary motions. Okay, however, I could personally read a book by Aristarchus. This book is On the Dimensions and Distances of the Sun and the Moon. And this book, even if written 3 centuries before Christ, is crystal clear and very clever and advanced. Okay, I will tell you quickly some ideas which you can find in the book by Aristarchus On the Dimensions and Distances of the Sun and Moons in the next slides. However, I want to tell you that Aristarchus was answering to an objection to the heliocentric theory, which is very deep, very, very important. They told him how it is possible that you see fixed stars if the Earth is moving around the Sun. Aristarchus had the right intuition to answer to this objection in this way. The distance between the Earth and the fixed stars is much greater than the diameter of the Earth's orbit. Okay? So, because of the famous parallax phenomenon, if stars are very far, you cannot see their motion, even along a period of 1 year when the Earth is running around the Sun. Now you understand the reason for which he was sticking to a scientific project to measure the dimensions and the distances of the Sun and the Moon. Unfortunately, Aristarchus died before completing his project. We will discuss this here, but one of his pupils could train another pupil who could train somebody who finally concluded this scientific project. Now, let us rest 1 second and let us start to introduce a little bit some mathematics, because, you know, we are not talking only about philosophy of science. We'll limit this only for a few lectures. Now, imagine to stay on the Earth and do observe alpha moon, exactly alpha moon. Okay, so the ideas of Aristarchus is the distance between the Earth and the Moon is much greater than the distance between the Moon and the Sun. So the rays of the sunlight arrives all parallel to the Earth and the Moon. Okay, this is also proven by the fact that you see a straight line when you see alpha moon. Okay, so you have an optical evidence of this. By the way, optics was being developed in this epoch, because otherwise all these observations could not be founded solidly on theoretical grounds, on theoretical foundations. Now, the angle beta you can measure because it is the angle between the dividing line between light and darkness of the moon and the center of the sun. You can invent a sextant for doing this. It is a very simple measure, but there is a very bad news. As the sun is very far from the Earth and the moon, beta is very close to P over 2. It's very close to alpha. Okay? And we know that the tangent is diverging. Now, the ratio between the distance, the ratio of the two segments, moon, sun, moon, earth, is clearly the tangent of beta. So if you measure this angle, you can estimate the difference, the ratio between this distance and that distance. Okay? But the bad news is that the tangent diverges close to pi over 2. So a small error in measurement implies a large error in estimation. For this reason, the estimate of the ratio between the distance sun, moon, and earth, moon, as given by Aristarchus, was dramatically wrong. Okay. However, Aristarchus not only invented the correct procedure for measuring this ratio, but invented also an algorithm to estimate the tangent of any angle. So, in a sense, he is one of the inventors of trigonometry. But look here. When you see the moon passing before the sun, so you have a sun eclipse, okay? You can estimate the m over mh segment divided he segment and the sh prime segment divided h prime e segment. Okay, simply measuring this angle. So you can find an estimate of the moon radius and the sun radius and link it to distance between Earth and moon and the distance between Earth and sun. So with this simple Euclidean geometry, you can start getting important measurements about the dimensions of the solar system. Now, 30 years after the death of Aristarchus, Hipparchus of Nicaea was born. Now, Hipparchus, by the way, this is a drawing representing Hipparchus made during the French Revolution. You can see that people during the French Revolution considered Hipparchus more or less as one of their contemporaries. The tools he was using were very similar to those used during the French Revolution, and actually this is rather true. Now, I suspect that the phenomenon occurred to Archytas of Tarentum work occurred also to the works of Hipparchus of Nicaea. His science was too mature, and therefore it was too complex to be passed on to posterity. Hipparchus produced very accurate models. Secondary sources suggest that his analysis is based on observation accumulated over centuries by the Babylonian Chaldeans. Hipparchus was the first to estimate correctly the distance between the Earth and the Moon using a measure of the duration of the moon eclipse. So now, let's go back so you understand. Aristarchus started measuring the ratio between the distance Sun, Moon, and the distance between Earth, Moon. Then he got also an estimate in terms of these ratios of the radius of the Moon and the radius of the Sun. Some 100 years later, 70 years later, Hipparchus manages to measure the distance between the Earth and the Moon. So he managed to complete the measurement of the distance between the Earth and the Sun without moving from the Earth. This is an example of the power of mathematics. You stay in Alexandria, you are clever, you invent a method using Euclidean geometry, and of course you need 5 generations of scientists for doing this, but at the end you measure the distance between the Earth and the Sun. How Hipparchus did this calculation? When you see an eclipse, you can calculate the time when the moon is passing in front of the sun. Okay, and then you can measure the angle, the apparent angle of the diameter of the sun from the Earth. Okay, so in this way, you can calculate the radius of the circle of the trajectory of the moon around the Earth. Okay. Okay, I will not go too much in these details. Those who are interested can, I will give you the references in case, but this is very interesting. By the way, I'm writing some long lecture notes on this, so all details of this will be written, I think, in few weeks, and I will give to all of you this paper. Okay. So at the end, he made mathematical models for predicting solar and lunar eclipses, and is one of the founder of trigonometry, which is systematically applied to the study of motions of the sun and the moon. Now, I want to tell you how sophisticated was the knowledge of Hipparchus. Hipparchus probably already knew, because Aristarchus most likely was the originator of the kinematic explanation of the equinoxes and solstices. So I need to explain you this shortly. So remember the circle of Nebra. Now we invented a kinematical model. Why kinematical model? Because up to now, we don't say anything about equations predicting these motions. We are simply describing the motions, okay? So after several centuries, Greek scientists developed a model of the motion of the Earth around the sun, whose basic ideas are the following. First of all, you have that the motion of the planet is planar. So you call the plane of this motion the ecliptic plane. Then the Earth is turning around its axis, but the axis is not orthogonal to the ecliptic plane, ecliptic plane. Okay. So what you have? You have that the 21st of December, the Earth is oriented in this way with respect to the rays of the light rays of the sun. So you have a bigger energy per unit area arriving in the south hemisphere and a smaller amount of energy per unit area arriving in the northern hemisphere. This means that north you have winter, south you have summer. The 21st of June, you have the other way around. You have that the higher amount of light is arriving north and the lower is arriving south. Of course, at the equator, you have more or less the same, so there is no true difference between the seasons, okay? Then, remark that the closest point to the sun in this orbit is close to the 21st of December, while the point where it is, the distance is maximum, it is close to June. Okay. Then you have two other days of the year in which this axis is in the plane made by the orthogonal direction of the ecliptic, and it is not orthogonal. You have that the plane made by the tangent vector, so the tangent to the curve and the normal to the ecliptic. In this plane, you have this axis. So what happens? That exactly one half of the Earth is in the light and the other half is in the darkness. And this is the line of equinoxes. Okay, so the inclination of the axis of rotation of the Earth is telling you, allows you to describe this alternance of equinoxes and solstices. Okay, so look how clever is this conjecture. In this way, you describe a phenomenon which is without any explanation in terms of a more sophisticated model in which you have the sun in the center and you have a complicated motion of the Earth around the sun. Okay. Now, you can define a sidereal year. This is the time taken by the Earth to orbit the sun once with respect to the fixed stars. So when you look at the fixed stars and you see them exactly in the same place, okay, you see that this, you can say that one sidereal year is passing. A tropical year, which is also called a solar year, is the time that the sun takes to return in the same position in the cycle of seasons, which we have described before. Okay? For example, the time from vernal equinox to vernal equinox, or from summer solstice to summer solstice. Okay? But, okay, the difference between the sidereal year and tropical year is 20 minutes. This is an observation. Now, Hipparchus describes this difference. Look, they could measure a difference of 20 minutes of the duration of 1 year. So they had very sophisticated clocks. Actually, water clocks were invented by Hellenistic scientists. Okay. Now, what Hipparchus of Nicaea manages to understand? Okay, Aristarchus knew the distinct values of tropical and sidereal years in 280 before Christ. Okay. 150 years after, Hipparchus explained this difference by means of a very simple conjecture. Okay. He claims that the rotation axis of the Earth around itself is changing its orientation in time, so that this axis is slowly changing its orientation with respect to fixed stars. Okay, so just to give you this idea, this is the motion, secular motion, because this happens with a velocity in which you see differences of 1 degree in a lot of time. What he did measured the ecliptic longitude of the star Spica during a lunar eclipse. He found that Spica was about 6 degrees west of the point of the autumnal equinox. So during this eclipse, a star can be seen, and he measured Spica, and he measured its angular distance with respect to the point of the autumnal equinox. The azimuth was 6 degrees different. In every Greek society, children are playing with a top spinning, with a spinning top. So most likely Hipparchus invented this toy in order to give an explanation of the precession of equinoxes. This is another conjecture. But if you think that Aristarchus invented the trick track for explaining the vibrational explanation of sound, you can say that this conjecture is not so strange. I mean, probably can be accepted. Anyway, the rotation, the axis of rotation of the Earth moves, and it points nowadays towards the polar star. In the 14th after Christ, in the 14th after Christ, it points towards Vega. So the orientation of this rotation axis changes slowly with time. Now, Hipparchus was not like modern students. You know, modern students believe that they know everything and they don't need to interact with ancient scholars who are all useless and old. I mean, old now means useless and not reliable. Hipparchus could compare his measurements with those of Timocari and Aristillus, 4th and 3rd century before Christ. Okay? And these authors had written the first star catalog. By the way, you should think about this. Some scholars, the 4th century before Christ, spent all their life for writing a star catalog, a totally useless activity for everybody for many centuries. Okay. So when somebody asks you why you are learning mathematics, you should try to explain them that we are working for the next millennia for producing evidence to be used in the next millennia. Now, Timocari and Aristillus had measured Spiga longitude at a 2 degrees difference. So Hipparchus made the conjecture that the stars of the zodiac had shifted over time, and with a trivial linear assumption, he estimated if 2 degrees in 150 years, then it means 48 seconds per year. Okay, now you must remark important, the actual value, I mean, actual means the one which we have measured now, and it is the most reliable, is 50.26 seconds. But remark that Ptolemy, 3 centuries later, estimated this shift into 36 seconds. You should not believe that knowledge is monotonous in time, monotonic in time, and that Ptolemy, which is later scientist compared with Hipparchus, is better than Hipparchus. Actually, we will discuss that Ptolemy probably was a kind of not very clever student of the school of Hipparchus. Okay, he was among the worst students of that school. Hipparchus also invented, he was a compiler of a famous star catalog, but he invented the astrolabe, which is the final evolution of nebra disk. Thanks of an astrolabe, he could place the stars and the planets at their place in every moment, estimating all angles which could be estimated from his latitude and longitude. Okay, Hipparchus observed the discrepancies between his stellar catalog and that compiled by Timocari and Aristillus, and obtained the clue to conjecture the precession of the equinoxes. So I want to tell you clearly, Hipparchus was more or less having the same tools as the people building this. Okay? He observed that when the sun comes exactly at the same place, you must wait 20 minutes before the stars arrive at the same place. And he conjectured, thanks to his predecessors, so Aristarchus and many others, he invented a model in which he describes this variation, observed discrepancy. He reduces these observed discrepancies to the motion of the rotation axis of the Earth. And then probably to prove that the mechanics of bodies produces this kind of phenomena, started playing with a spinning top. We are nearly ended with Hipparchus. He was really a giant, because Hipparchus described a nova. he could observe the explosion of a nova. And therefore, he conjectures that also the fixed stars were not fixed. They simply seemed to be fixed because they were very far from us. Okay. Now, we must conjecture that another big scientist, Seleucus of Seleucia, gave some extra contributions to mechanics. And I think that the contribution of Seleucus was mathematically and mechanically very important, because Plutarch, who is an historian of later historian, wrote that Seleucus had demonstrated the heliocentric theory. So what it means that he demonstrated the heliocentric theory? Probably it means that he had some basic principles of mechanics, more or less as we have the law which we call Newton's law of universal gravitation. And from this law, he deduced that the planets must move around the bigger mass, the sun. Unfortunately, we don't have Seleucus books, okay? What we know is that he studied the tides and managed to link them to the motion of the moon and of the sun. Not only, we know that he supports the concept of infinity of the universe. He claims that the universe is infinite. And Galileo is most likely quoting him when he talks about an ancient Greek scientist describing the motion of the tides. Okay, I think, you see, this drawing is in a hidden way introducing the concept of force and giving you the idea that forces are kind of arrows, okay? This is something which I will criticize later, but for purely pictorial reasons, we can accept to use this drawing for the moment. So Seleucus describes the low tide and high tide phenomenon compared with the low tide and high tide phenomenon, because you know you have some high tides which have a very large amplitude, some high tides which have a smaller amplitude, and you have low tides which have smaller and higher amplitude. So the idea of Seleucus is the water constituting the oceans are gravitationally attracted by the sun and the moon, okay? And when the moon and the sun attract the water of the oceans in the same direction, you have very high tides, okay? When the moon is orthogonal to the sun, then the high tide is towards the moon. However, its amplitude is smaller. So you understand that if Seleucus must be the man who demonstrated Aristarchus' heliocentric conjecture, and if Aristarchus is the one who described in a careful way the tides as the result of the interaction between moon, sun, gravitational interaction between the moon, sun, and the oceans, then Seleucus had to have an idea of the law of universal gravitational attraction. Okay. This is another conjecture, of course. Okay. I have found some scholars who claim that Seleucus had linked the magnitude of the tides to the distance between continents. By the way, it is sure that Seleucus knew that the tides in the Pacific coast of Africa are bigger than the tides on the Atlantic coast of Africa. Okay, so clearly the amount of water which can be moved differs, so that you can easily connect the distance between continents to the amplitude of the tides as observed somewhere. So it is not impossible, let us say in this way, that Seleucus could have estimated the distance between Africa and the continent on the other side. Of course, he did not call it America. He could have called it in another way. Okay? Okay, now, before we end this lecture, we must describe a very strange phenomenon which occurs very often when mathematics is too complicated to be understood by some generations. Now I must tell you this. I was teaching several years to environmental engineers at the University of Rome. And a delegation of students came to me to tell me that I was obsolete because I wanted to talk too much about matrices, determinant of matrices, inverse of matrices, linear systems, the theory of the rank of matrices, Rouchet-Capelli theorem, and this kind of thing. Please, if you have some doubts about what I mean with all these names, go to give a glance to your books dealing with these subjects, because we cannot survive this course without talking about linear algebra. Okay, linear algebra is one of the essential prerequisites. Another student came to me and he told me that the theory of beams by Saint-Venant, which is the theory which explains you how a beam is bent under external loads, is useless. Because his father, who is a brick layer, somebody who can build walls, knew very well how a beam is behaving. This same person, I called him for 1 whole year Sextus Empiricus, came to me and using exactly the words by Sextus Empiricus, you know, this man was clever because he invented alone an ancient philosophy. Okay, he came to me telling me that the theory of elastica, the theory of elastic curves, is meaningless. Why? Because you cannot have something which has no thickness. So the theory of elastic curves doesn't mean anything. Sextus Empiricus. 160 years after Christ, he died 50 years later, wrote all these books here against grammarians, against rhetors, against geometers, against mathematicians, against astrologists, against musicians, against logicians, against physicists, against moralists. So he took all the theories available in his epoch and he said that it was all garbage, a total garbage. Okay. Sextus Empiricus is one of the first known politicians claiming that university professors are useless. Okay? And knowledge and science is useless. There are some in Italy in this moment, like that man called Salvini, who made crazy laws. Now I have a professor, a friend, who is full professor in Cagliari. He got a nomination by the Minister of Research as one of the biggest experts in mechanics in the world, and he got the position as professor in Cagliari without any competition, because the minister recognized he's an outstanding genius. Okay, he arrived in Cagliari and now he's obliged to see some girls who should teach him how to be integrated in the Italian society. They were teaching him the Italian constitution, okay, but they were wrong. So he corrected them because he knew Italian constitution better than these presumed teachers. When you arrive in a society, when you arrive to state that knowledge is useless, and when you start treating full professors like workers building walls to whom you must teach basics of civil life in a society, then you are in troubles. Sextus Empiricus wrote that thought things do not exist. Mathematical definitions are not necessary. Mathematical entities do not exist. Moreover, he says that no mathematical concepts exist because bodies exist, but incorporeal things do not exist by definition. So, in a sense, as it was too complicated for him to understand the definition of real numbers, he decided that real numbers do not exist because they are invented by human mind. Okay, this is a delicate issue we will touch in one of the next lectures. What I want to say, is that the existence of the sun and the existence of real numbers, I can agree with you, we are talking about two different kinds of existence. Okay? The sun exists in the real world. Real numbers exist in our mind. They are invented by our mind. Okay? But they do exist. Okay? But what is astonishing is that Sextus Empiricus said exactly what my student told me when talking about the Elastica equations. A segment does not exist because nothing has no thickness. A geometric point does not exist because no body object has no dimensions, but only position. A surface does not exist because every body has thickness. So what happens? In Sextus Empiricus, the confusion between model and modeled object is so complete that it leads to the rejection of the concept of mathematical model. So what happens is simply this. When you have a ball rolling along a guide, you may decide to model the guide as a surface which cannot be trespassed by the ball. This is a modeling simplification. Of course, if you take the ball and you throw it violently against the surface, then the surface will be deformed, or the whole body constituting the surface will change its shape. So the model of surface will not be suitable for describing the impact. Okay, so a mathematical model is capturing some features of the phenomenology we are interested in and uses only the relevant features in some specific phenomenon for getting a simplified description of this phenomenon. So this is the crucial point. By the way, during Middle Age, they already understood that Sextus Empiricus philosophy was destructive. In fact, this is a drawing where you have a pig eating on this boat. Philosophers of the school of Sextus Empiricus discussing about the fact that wind is not existing and it is only the imagination of perception, and the boat which is sinking. So I think it is really important that students study some basic philosophy, because in this way they will not reproduce in their mind the mistakes or the false behaviors which has been already conceived in the past. Let us be wrong in another way, my dear friends. Let us invent new ways of being wrong. We should not reproduce systematically the mistakes of our ancestors. Okay. Okay, today is the day of the woman, so it is necessary that we talk about Hypatia. Hypatia is later than Sextus, so her existence proves that the school of mathematical physics in Alexandria did survive the criticism of Sextus Empiricus for a while, but it did not survive a mob of Eudoxus Christians who killed her. So she can be considered a martyr of freedom of thought. What happened? It is like nowadays in Italy during the vaccine COVID infection story. You know, a politician who studied only few years after elementary school dared to say to the president of the Accademia dei Lincei, who is a famous theoretical physicist, who got several nominations to Nobel Prize, who got Wolf Prize for his discoveries, who, by the way, is a great expert in complex systems. Okay, this group of young people activated by this politician said that a physicist cannot discuss about the predictions concerning infection. Okay, these people do not understand the fundamental difference between the equation of diffusion of a disease in a large number of individuals and the mechanism of infection from one individual to another, and the required medicines for saving a person having this infection. In this world of extreme specialization, you need a medical doctor for giving you medicines and trying to save you if you get COVID. Okay? You need an expert of fluid dynamics or a clever virologist for understanding how a virus is transmitted from one man to another, a human being from another human being, okay? And you need a theoretical physicist for predicting, given a certain modality of infection, the speed of evolution of infection in a group of humans. Okay? The same, if we had a different society, these people could kill the president of Accademia dei Lincei, as happened to Hypatia, shouting that he wants to destroy restaurants. Okay? Now, it has to be remarked that Hypatia managed to succeed her father as a leader of Alexandrian community. Probably the museum and the library no longer existed at the epoch of Hypatia because a Roman emperor, Aurelian, had destroyed them. Okay. Now, we don't know exactly what she wrote because the sources, her books were destroyed. However, Klein, a famous British historian of mathematics, said that the Alexandrian school possessed the unusual combination of theoretical and practical interests. It enjoyed complete freedom of thought, which is an essential element in the flourishing of a culture. What now I want to state is that it is not true what you find in many books of history of science, that Romans were engineers without any knowledge of science and scientific. They had no scientific theories, while Greeks were great theoreticians, incapable to invent practical applications of their theories. This is absolutely fake. Okay, and I will give you an example soon, a practical example soon, but Klein claims that the Alexandrian school could combine theoretical and practical interests. Okay, by the way, the fair, the farum, which is the Latin word for the sea light, okay? Farum, fair, was the name of an island in Alexandria. They built a lighthouse, a very big lighthouse there, and this lighthouse was sending its light far, very extremely far, and it remained there for several centuries because of the mirror system which was built inside it. So optics for Greeks was not a mathematical game, was a way for building lighthouses, okay? And mathematics was a way for measuring the distance between the Earth and the Sun, for instance, okay? Klein concludes that Alexandrian school made important advances in numerous fields that were to become fundamental in the Renaissance: plane and solid quantitative geometry, trigonometry, algebra, infinitesimal calculus, and astronomy. I think that we are starting to be a little bit tired. So as a first lecture, we should conclude, but before we conclude, I want to give you the final proof that Greek theory was not only theory, but was practical. The astronomical calculator of Antikythera dates 150 years before Christ. Okay? It has been found in the island of Antikythera, down in the sea, inside a sunk boat. This mechanism is here. I mean, you have pictures of it, okay? Its mechanism has been fully described. Instead of talking about it, I want to show you a nice movie I found in the web. Okay? And this is the mechanism as it has been found. Then they reconstructed, so you have the mean sun wheel, which turns in 1 year. Then you have the input wheel. Then you get the calendar gear train. Okay? Then you get the eclipse gear train, the lunar anomaly platform, lunar gear train, the lunar eccentric couple. Then you have some cycles used in Greek calendar, in particular the Olympic Games. Okay. Then you have the back dial. Okay. Here you have the eclipse prediction display, the calendar display. Then you have the way in which this system was mounted. And you have the Venus, Mercury epicycles. Okay. Then you have the wheel of annual motion. Then you have Mars with its epicycle, Jupiter. Okay. Then you have Saturn. And then the zodiac with azimuth. The calendar, and then you have the wheels giving you the motion of all planets. This is the extreme evolution of the Nebra disk. Turning the wheel, you can see the motion of all planets in the azimuth. The moon, the planets, the phases of the moon, the sun. Okay. I conjecture that with this tool, one could also estimate not only the latitude, but also the longitude. Okay? So, the statement with which we stop now, today, is the following. The knowledge is not accumulated and stored forever. You have declines before you could build again a mechanism like Antikythera mechanism. We needed to wait for French Revolution. So we had a long decline and a very slow recovery of knowledge. Okay? So tomorrow we will see how the decline produced the materialization of not Aristarchus model. You know, Middle Age materialized Eudoxus wheels. Eudoxus model. So at the end, we will see this, we'll discuss this in greater detail tomorrow. At the beginning of Middle Age, some scholars believed that in the sky, there were some metallic structures on which somebody had hammered stars. So we get what we can call an extreme materialization of a mathematical model. So they confused the analog computer used for predicting the motion of the planets with the physical reality. And dear friends, be careful, because I have seen some students confusing console, SAP, Abacus, some software with the reality of physical objects. And this is very dangerous because there is no mathematical model describing everything which happens in nature. So you will never stop inventing a better model for describing in a better way the phenomenology. Okay? So I think that these are very important subjects which I was discussing in the last years during the course. And I think it is worth that we clarify them at the very beginning. And as I know that some arguments will be a little bit difficult, then we will discuss at the end also of the course another time, trying to use all mathematical tools that we had understood during the course, hopefully. Okay? Okay, so next lecture, we can stop recording and